Welcome friends. So, this is part 2 of the course defects in crystalline solids. The name of this course is this is part 2 of this course. There is also part 1 of this course, and if you have not taken, you need not worry, these videos are still available and you can still go through this course even as a registered candidate. And just so that there is a continuity, you can visit the part 1 course, go through the videos, understand the concepts and come to part 2. Now about this part of the course. So, first what we covered in part 1 of the course. In part 1 of the course, we covered the fundamental aspects about two major type of defects that are found in crystalline solids. One is the point defect and the other is the line defect, which is dislocations. So, we looked at their fundamental aspects. What is this purpose of this part 2 of this course? In the part 2 of this course, we will look at the advanced concepts and in particular these line dislocations in particular type of crystal systems. So, we already had a brief look at dislocations in FCC and BCC, but that was just a brief glimpse. We will now take a look at it in a more detailed and complete view of the dislocations that exist in not only in FCC and BCC, but also in HCP, then also in superlattices and in ionic crystals. So, that is one important module of this course, and another module in this course is to relate these concepts to some of the important observations regarding properties of the materials. For example, yield point phenomena, I mentioned this is also in the part 1 of the course, is an important property that we observe, but this is not arising out of nowhere. It is arising because of interaction between dislocations or the line defects and the point defects, which is the vacancies and also solutes. So, this is just one example. Then also you have low angle grain boundaries that you see, that exists in materials, and that is again nothing but array of dislocations. So, we will look at this, and also another important aspect is strengthening effect. Now, why does strengthening take place in materials? Most of the material, the strengthening takes place because some way or the other dislocations or motion is getting restricted. Sometimes it may be a precipitate, sometimes it may be a solute, sometimes it can be other bunch of dislocations, which is called forest dislocations. So, all these together give rise to strengthening mechanism in strengthening phenomena in metals and alloys. So, we will look at these two. So, with that we have set the contour of what will be covered in this particular course. Now, let us get started with a more detailed understanding about dislocations in FCC system. So, to begin with, as I mentioned even in the first part of the course, that when we talk about dislocations, the dislocations are usually in the first part we had a very simple view of this. So, these are planes of atoms. Okay. So, these are not just lines, these are planes of atoms, and there is somewhere extra half plane, and below you can call a missing plane, and this missing plane where this extra half plane ends, we call that a dislocation. And we also had a brief glimpse at how this would manifest in FCC system. We found that this simple system is not true for FCC. What is different is that there are two missing planes instead of one. Another thing that we learnt was that we did not again look at it in the last lecture, we did not go in the detail, but another thing that we found was that this Berger vector, we usually say that Berger vector is always closest packed direction. Well, in general it is true, but in here you would see that this can also dissociate into partials. So, the two important things that we will want to look at is one, that there are more than two planes instead of one when we talk about the extra half plane or the mixing plane, and that it can dissociate, the dislocation can dissociate into partial. Now, with this point in view, what I have done is I have prepared a very nice PPT which will give you a good understanding of what is this, how this, there are two missing planes and how the dislocation can dissociate into partials. So, let us look at this. So, this is our presentation that I will show over here. What we want to show are two extra layers for planes and that partial dislocations. So, now let us look at what is called as a ball and stick model for FCC. So, as you can see, this is a cube and at the corners you have the atoms and the atoms are at the face centers. Here the x, y, z axis are defined. So, this is the x, this is y and this is the z. This is how we have defined, and you can assume that the center lies over here at this corner. Now, where is the 1 1 1 plane? Now, we are not talking about a family of 1 1 plane, we are talking about particular 1 1 1. So, all positive 1 1 1. So, if this is 0 0 0, so this becomes y 0, this is y 1, this becomes x 1 and this becomes z 1. So, we have to connect these and okay. So, before that this is the 1 1 1 direction, and in a cube 1 1 1 direction would be normal to 1 1 1 plane. So, this is your 1 1 1 plane which is shown as blue colored. Now, here as you would note that this is not the only 1 1 1 plane, you could have drawn it at other locations also. So, for example, you could have as well, this is parallel, we can draw it like this. Okay. So, this is also 1 1 1 because if you move it, which is translated by a small vector in this direction, you would see that it overlaps. So, this is also 1 1 1 and inside the same lattice, inside the same cell, and you can even draw it, or there will be still parallel 1 1 1 plane which will pass through the atom over here, the one where I am highlighting. So, there are, if you look very closely, you would realize that there are three different layers, and why we are calling layers, because the arrangement of atoms when you look through the 1 1 1 direction is a little bit different. We always show this as the 1 1 1 plane. So, here you have so as you can see, this is one line and this is another line, and you have atoms which are representing the corner atoms and these are the face center atoms. And with 1 1 1 particular orientation or 1 1 1 plane, we can call this as 1 bar 1 0 direction, this as 0 bar 1 1 direction, and this as 1 0 bar 1 direction. So, these are these three direction. If you again look at the blue one, the blue plane, so we are talking about this direction, then we are talking about this direction, and then we are talking about this direction. These are the three directions shown over here. We will come back to this why I have drawn it, because we will need it again and again. Now, this is the ball and stick model. Now, we can draw to, in order to understand the three different layers, we can draw it also in what is called as hard sphere model. So, this is a hard sphere model. Now, you remember in FCC, which is the closest packed direction, the closest packed direction is the 1 1 0 direction, and all the atoms along this 1 1 0, as you can see, are touching each other. So, in here all the atoms are touching, which is how it has been drawn. So, this is 1 1 0 kind of direction, this is a 1 1 0 kind of direction, this is a 1 1 0 kind of direction. So, this represents our 1 1 1 plane, and these are direction, like I said, this is the triangle. If you relate it with this over this triangle over here, then this triangle is what is over here, and it is drawn in hard sphere model. So, we are showing them touching each other, which is what is expected in a FCC, which is closest packed structure, closest packed cubic structure. Now here this is the blue layer, which is the first one over here. So this is drawn as, this is, let us call it layer A. So this happens to be our layer A. How would layer B look like? This is layer B. What is different here? Actually, if you look at it independently, there is nothing different. This blue layer, which is shown in red or pinkish type of color or orangish color, this is exactly same orientation. Here also you would see the triangle where the sides would represent 110 direction. But what will be different is their relative orientation with A. Similarly for the C layer. Now this is the C layer, which is green in color, and here also the as an individual layer, the orientation of atoms are exactly same. So the atoms are touching each other and they are touching around along the 110 direction, as you can see. So this is these are your 110 direction, and if we call this as the normal of this is 111, then we can specifically say which direction is this and which direction is this, as we showed in the first slide. So these are three different layers, and like I said, independently looking at it, there is no difference in any of these layers. What is different is when you place them one over the other. Now let us put B on top of A. Now if you had the blue layer, which was our A layer, so A layer was this blue layer, and as you can see there are different kinds of points where you can put the next layer, or where the, you can say, trough lies, where another sphere can fall into. So these are these different troughs, but you cannot fill all the troughs, you can only fill half of the troughs, and other half trough will remain empty when you put another layer on it. So you can put your layer either here or here. So we can say there are two positions, and one of these positions will be taken away by the B layer, which is the red layer. So these are the ones which have been taken away. So you can see these layers have been taken away and the alternate ones have been left empty. Whenever you have another one layer falling onto this will happen, that only one particular set will be taken, or one set position will be taken. So now we have A and B, B is on top of A. Now where do we put C? Now when you try to put C, so when you put B on top of A, there is no particular, you can say, preference of which one should we take. You can select any of these two. But when you come to C after putting B, then there will be a distinction between two possible sites. Now here also you can see these are one set of possible sites, these are another possible set of possible sites. And what is difference between these two? So I have called one as position 1, the other as position 2. What is the difference between these two? You would see that these particular points lie in a empty region. So the A layer are not below this, but position 2, if you look at it, there is atom A over here, not atom A, layer A over just below it. So just below this is layer A. Now this clearly means that the two sides are very different, and therefore there will be different preference for this. Which one do you think would be energetically preferred? Now if you put over here, what will happen is that A layer and C layer will be one on top of each other, very close to each other, and therefore there will be a lot of repulsion. But if you put C layer in this vacant region, then that repulsion would be minimized, and therefore clearly this position 1 would be preferred in terms of minimizing the repulsion. So let us put C layer on top of it. Now this is what we can call as the ABC layer that is found in FCC, and it is called ABC stacking. So ABC, another layer will come just on top of ABC. So this will give you the what is called as ABC stacking of FCC. Now if you have selected position 2, how would it look like? The green atom would fall right on top of blue atom, and it will look like this. So this will be green on top of blue, and so you are able to see only two layers, the B layer which is reddish in color, and the A or C layer which are same. So, this is called AB type of packing, because now you have only two different positions here, A and B, the third again goes on top of A, and actually there are crystal systems where you see this, and it is HCP systems. In HCP also you can get AB type of packing in the 0001 direction, you get AB type of packing in HCP. So, this is the HCP type of system. Now, let us come back to our ABC layer of FCC. Now, where is our 110 direction? So like I said, these are our 110 direction, and these are what? These are if you look at just half of it, this will become your Berger vector. So, ideally these are your Berger vectors. Now, if I take a edge dislocation with this as the Berger vector, then what should be the orientation of the line direction? If this is the Berger vector that of the dislocation that I have selected for a edge dislocation, then the line vector must be perpendicular to this, and the line must lie something like this. If this is the dislocation line, then where is the extra half plane or the missing plane? The missing plane is lying just above it. Okay. So, we somewhere over there the missing plane will stop, and above it there will be a missing plane. So, this will be the, let us say this is just the line, and therefore, the missing layer stops here, or the extra half plane which is below it just ends over here. So, this is our dislocation line, and where our missing plane ends or the extra half plane ends. Now, how will it look like? This is how it looks like. So, there is one layer of missing atom, one atom here, one atom here, here, this. So, one layer of atom has been moved, but then what you would see is that this is not really one layer of atom that is missing. You connect straight lines, all these connecting points where the atoms could have lied, this, and similarly over here. So, this forms one set of planes, and this forms one set of parallel plane. So, earlier our conviction that there are two missing half planes is now proved over here. This is our Berger vector, and this is where the extra missing layer of planes are missing, and it forms two layers, one along this line and one along this line. So, there are two layers of missing planes. So, one thing we can clearly see that now, and this forms one whole dislocation. Now, let us come to another aspect, which is the partial dislocation. So, here what you see? Here you see that this dislocation, this is what the Berger vector is, and the atoms would like to move from here to here, and then it will have actually moved one atomic plane, which is how the dislocations glide. So, ideally this is the Berger vector that it should follow, but then what you would see is that although this is the shortest vector, but in terms of the lattice parameter, but there is still another shorter vector, and if you find the magnitude of this, you can very clearly show that this would be like this, of the type A by 6 1 1 2. We will come to that again in a little bit later. So, this is your another partial, not partial, we will not call it partial, we will define it later on, but this is I am just showing that this is another possibility. So, this is the original vector, and there is a possibility that instead of going directly, the atoms would move over here and then move over here. Let us see how it does that. So, here you see the atoms have moved from in that position to this position. So, this position to this position, and from here they can again move over here. So, the whole dislocation line has moved from over here to over here. So, let us come back again over here. So, this is we said there is two missing planes of atoms, and ideally dislocation would like to move along the 110 direction, but it so happens that in this particular configuration there is even a shorter route possible. Now, we have to find out, we will see later on, but not right now, we will show that A/6 112 path is energetically favored, and that is, if you look at the energy relation between the original Berger vector and the two smaller Berger vectors, then the sum of the two smaller Berger vector energy comes out to be smaller. So, this would be a possible feasible path, and geometrically also we see that this is feasible. So, yes, this does happen. So, as here also I have shown that 1/6 or A/6 112 direction are the smaller green arrows. In usually, why would you not prefer it, or why this would have any kind of, you can say, resistance? This is because the third, when you go from in this particular fashion, when you move from this place to this place, what actually has happened is that the atoms have moved away from position 1 to position 2. So, the C layer, this extra half plane that we are talking about, is not lying on the C position, which was the position 1, but it is now lying on position 2, which is right on top of blue. Now, you can see clearly here, this is the green atom and just below it is the blue atom. This is the green atom, just below it is the blue atom. This is the green atom and just below it is the blue atom. Similarly, all these atoms that you see over here are lying on position 2, which is, you can say, is not the preferred stacking sequence. So, now it has become AB in this A. So, there is no C position in this for this particular layer. On the other hand, your remaining system, it is still following that ABC. So, the other part is not concerned about how they are oriented in between. So, the only resistance to forming these partials would be the stacking fault energy, and we will see that in more detail. So, we have this full dislocation over here, and we have moved just one layer, and when you move another layer, when you have moved just one layer of atom, what you see is that the two lines that we drew can now be separated into two parts. One is to the left of this extra layer, and the other is to the right of this extra layer. So, now in a way, what we were calling as two planes together for the extra half plane have now dissociated. They have come into two parts, and this is what we can define as partial dislocation. So, the Berger vector for this partial dislocation would be this one. Similarly, the Berger vector for this partial dislocation would be this one, and when these two come together, then we have this as the Berger vector of the full dislocation. So, here I showed that it can move back, and then you have completely displaced the extra half plane or the missing layer by one atomic distance. So, this is what you would ideally expect, but now let us get back to this position and where these two partial dislocations are over here. Now, let us assume that there is some amount of repulsion between these two. Now, these can behave like two different dislocations, right? They are now they can be treated as independent dislocations, and since they have they have some components similar to each other, so there will be net repulsion. And this is one dislocation, this is another dislocation, and they will try to repel each other. So, what will that repulsion do? That repulsion would lead to something like this, meaning what has happened, what changed here? There is another layer of atom that has moved. So, this line has moved independently. Now, it is not connected with this, its movement is no more related with the left part. The right one has just moved to one step right, and it has allowed another layer of atoms to move over here. So, you can see that there is a dislocation line over here, there is a dislocation line over here, and in between these you have the region which is, if as you remember, does not follow the desired sequence of atoms, which is ABC. It has ABA type of sequence. So, this region can be called as stacking fault region. And onto the left of this we have the perfect crystal, onto the right of it we have the perfect crystal. So, a full dislocation line has got dissociated into two partials, and assuming that there is a net repulsion, which we will see later on when we come to the mathematics of it, assuming that there is a net repulsion, these will keep moving away, and they will keep moving away, and there will be a stacking fault region which will have some energy raised. So, this is a stacking fault region, meaning there is a 2D defect along with this line defect that you see, two line defects over here. A 2D defect is being created in between this, which is called a stacking fault region, and there will be some energy associated with this stacking fault region. Now, how far these dislocations, the partial dislocations move, that will determine how long this stacking fault region is, and the larger the stacking fault region is, larger would be the energy. So, in here what will happen is that there is a net repulsion acting, which is trying to put the dislocations apart, and there is a stacking fault energy being created when the dislocations are moving apart, and therefore, that will try to keep this to the minimum, and therefore, there will be a balance created which would lead to a equilibrium thickness or width of this stacking fault region. We will come back to this in the later slides. So, in these particular slides what we have shown so far is that there are two extra half planes, and that these two extra half planes act where they can move apart and they can form partials. So, both these things we started to show two things, and now we see that those two things are related. What are those two things? That a full dislocation in FCC, the edge dislocation contains not one extra half plane, but two extra half plane, and then second part that these two, that it can form partial dislocations. Now, we see that these are because of these two extra half planes, the two extra half planes can move apart, and therefore, and they can keep moving apart, and they will act as independent dislocation or the extra or the partial dislocation. So, I will end this over here and we will come back to mathematics of understanding the stacking fault energy, the equilibrium stacking fault energy width of this dislocation. Okay, thanks.